This is Unit 6, Section 6.6, Area of Regular Polygons, Day 1. So we were practicing classifying polygons, and now we're going to look at the area formula to find the area of any regular polygon. So just like we had a rectangle, a square, a polygon, or a parallelogram, where all three of those have the same area formula, base times height. An even triangle takes base times height divided by 2. We're going to look at something that's consistent for all regular polygons, whether it's a decagon, a 100gon, a pentagon. Any of those will follow a pattern breaking down from what we can do with any regular polygon. So we have some vocab here to practice as we get started. But one of the things I want us to recall is the vertex. Again, is the kind of the corner of our polygon. So that would be like, here's a vertex, here's a vertex, here's a vertex, here's a vertex, okay? And it could be the corner of an angle too. So if I was looking at this vertex, we would consider this the vertex of an angle measurement here. Perpendicular, we're going to say, is a segment that forms a right angle. With another segment. And so we're going to make sure that we have this perpendicular idea where we have a line drawn into the side. And so we'll talk about why we need those pieces here. So recall, we've talked about the central angle, which we said, okay, we can find any central angle by taking 360 divided by n, the number of sides. And that's an angle whose vertex is the center and sides are radiuses. So if we look at this, we would have from here to here, this measurement is our central angle. The next piece of our polygon that we're going to use is called the side, okay? This is a segment that I've been referring to already, and that is the exterior edge of the polygon. So when I look at this, here's a side, here's a side, here's a side. And in this case, because we have a hexagon, I'm going to write this 6 times. Here's a side. So we have 6 sides on our hexagon. And then when we look at a radius, this is also another segment, okay, that connects the center to the vertex of the polygon. So now the radius goes from the center to the vertex. So this is a radius that's been drawn in, and so is this over here. And so if I drew in another one, this would be 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 another one. There's also 6 radiuses here, 6 sides, 6 vertices, 6 radius. And then the last one we have is the apothem. This is a 3rd segment, and this is going to be connecting the center to the midpoint of the side. Okay, so now I have from the center to the midpoint of the side. So this is called the apothem. From here to here. And so notice that if it's the midpoint, I know that this apothem has divided this into two parts and created that perpendicular measurement. So all of these parts are on a hexagon, but I could put these same parts on any of the figures. So if I wanted to do this for a pentagon, I could do this same thing where I would have a side here, a side here, a side here. Okay, I could draw in all the radiuses. Here would be my central angle that goes radius to radius, 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 and straight down. Here would be an apothem. Okay, and so again, if I did this with yet another figure, if we picked a decagon, where now we have 10 sides. So now I have all of these sides that I could look at, and they're all the same measure because these are regular polygons. I could have a central angle up to here, down to here, where I connect two radiuses and draw down the apothem. This makes a taller, skinnier triangle here. But it doesn't matter the shape, and that's what we're going to use to our advantage. Because if we can keep the consistency here, we don't need a different area formula for every single different polygon. So when we have all this information, we can start to look at the area of a regular polygon. And so there's two steps. Find the area of one triangle. So what I'm going to do is going to find the area of this triangle. And so notice it's base times height, which is my side length as the base, and the height of that triangle is the apothem. So if I know the area of this triangle, I can then multiply that area by the number of triangles in the figure. So if I took this and multiplied by 6, it would give me the total area, because every single one of these triangles is the exact same. So if I took this and rotated it, keeping this here, I would do one here, a second one, rotate to keep it at the center. Here's my third one, and so on. And so each one of these, I would have 6 of them because it's a hexagon. If I did the same thing here, find the area of this triangle here, well, there are 1, 2, 3, 4, 5 of this exact same triangle. So if I can find this triangle's area and multiply it by 5, it gives me the total area. That's what makes this consistent. Even with our decagon here, if I find the area of this whole triangle and then multiply by 10 for a decagon, it gives me the total area of the entire figure. So that's our goal today. Sorry. Let's look at applying this. We have this formula that says, okay, we're going to take overall, the area is going to be the area of the triangle times n, which is the number of sides. So we have this times n. So our goal is to know what the side length is, the apothem, and how many sides we need. All right, so our example on the first one, how many triangles are there? Okay, so this one kind of throws us off because it is a triangle to begin with. But if I divided it into 1, 2, 3, inside I would have 3 triangles here. The side length they've given us is 24.2. The apothem is known. That goes from center to the height, the perpendicular side here is 7. And if I know those two things, I can find the area. My triangle is going to be that base, that side length, 24.2, times the height, 7, which is our apothem, divided by 2, times 3, how many of those triangles we want. So 24.2 here, same triangle here if this was 7, same triangle here if this was 7. And so I want 3 of these triangles. So base times height, and then divide by 2 times 3 for the triangle. So when I put this in my calculator, I get 254.1 for my total area. And that would be measured in feet squared. On number 2, okay, if I drew in my triangle, central angle, how many triangles are there exactly like this? 1, 2, 3, 4, because it's a 4-sided object. The side length, okay, so now they tell me that side length is 8. And then the apothem, if I draw this in, draw straight down center to side, is 4, which means I have enough to find the area. Area is going to be base 8 times height 4 divided by 2 for the triangle, times 4 for how many I want. Because there are 1, 2, 3, 4 of this triangle here. Put that in our calculator and I get 64 units squared. So one of the things that kind of throws us off is that this is a square. If I know the side length, can't I just take 8 times 8? Yes. I wanted to show you that it works for all polygons, even ones that we might have had another rule for. However, if I know the side length of a square, I'm not likely to do this method, but it helps us for any polygon, whether it's a triangle, square, which I don't think I would use this complicated formula with, and then pentagon, hexagon for everything else. On number 3, okay, so how many triangles will there be? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have 8 triangles here. Side length, they tell us, is 13.3. Apothem, okay, so if I draw that in, they've given it to me over here, but it's going to be the same no matter where we are. I just typically draw it straight down, so I have it here. So I always kind of look at the same triangle that I'm drawing. So they said the apothem is 16, so if I have those pieces, I can find the area. So this is going to tell me that I have a base of 13.3 with a triangle height of 16 divided by 2 times 8 triangles that are identical to this one. Put it in my calculator and I get 851.2 centimeters squared. All right, so on each of these, we weren't missing any of the parts. And in fact, on none of them did we need to use the radius, even though on number 2 it was given to us. But we didn't need it as part of our measurement down here. So one of the things that we're going to look at is on our examples over here, we might be missing a piece, where here we only have one number given. And on number 2, one number given, and on number 3, one number given. So that's why we're going to spend 2 days looking at this, because I want us to see a couple different approaches to what can be or not be provided. All right, so on number 1, we still have the same questions over here, and our goal is to find the area. So when I look at how many triangles we have, 5-sided, 1, 2, 3, 4, 5, 6-sided object, we now are adding this one in, which is our central angle. So if I divided this, I have a central angle. That would be 360 divided by 6. Okay, so that would be 360 divided by 6 is 60 degrees. So this measure, the whole thing across, is 60 degrees. Side length, I don't know what that is. It's not given to me in the picture, but I need it to find area. What they did give us is the apothem. So we still know that this is 5. All right, so how do we find our side length? Because we need these two in order to find the area. What we're going to use is, do you see this right triangle here? This is why we reviewed SOHCAHTOA and special rights on the previous section. By looking at this triangle, okay, I have a 5 here, and the whole thing across is 60. So if I divide that in half for my triangle, that makes this 30 degrees. So I can use special right triangles or trig here. Okay, I need to find this piece, what this is missing. So if I use this, I can double it to find the whole side length. and that will help us with the area. All right, so I'm going to label this. I have circle and label, opposite and adjacent, and do trig. Tangent of 30 equals opposite over 5 and cross multiply. X equals 5 times tangent of 30, and that gives me x equals about 2.9. All right, so if x is 2.9, that's this piece here. So from here to here is 2.9, but it would be the same thing over here, 2.9 as well. My total side length now is 5.8. That was the other piece that I needed to find in order to get the side length. So I had to use trig to help me find a missing piece. Where on these three, everything was given to us. We didn't need any trig to do that. So once I have my base and my height, I can find the area. The base of my triangle is 5.8 with an apothem of 5 divided by 2, and I want 6 of those same triangles that are here. There'd be one here, here, and so on. When I multiply that out in my calculator, I get 87, and my units here will be meters squared. All right, on number 2. Okay, so we have our triangles inside of a triangle. Okay, so I'm going to kind of draw that in. So I have 3 of those for 3 sides. The central angle, I'll take 360 divided by how many there are, which tells me 120. Okay, so I know that this angle measurement is 120. The side length, okay, outside of my circle or outside of my triangle, I don't know it, but they did give me the apothem. They're telling me from center to side is 18. All right, so I'm going to draw that in here as well. This is 18. All right, so we still need side length to find our overall goal of area. So I'm going to go back to this triangle that I have here, okay? And so when I take this triangle out and look at it here, I have 18 here, and then the 120 also got split in half. So if I take 120 as all the way across and divide it with my apothem, this becomes 60 degrees. All right, so if I can use that to find this missing piece x, I can use it to find my entire side length here. So in my setup, I'm going to do opposite and adjacent and use tangent of 60 to find x over 18. Cross multiply, I get x equals 18 tangent of 60. So x equals, I get a decimal 31.2 if I'm rounding this and not using the radical. All right, so some of you might have noticed on number 1 and number 2 that these are special right triangles. If you see that pattern and can say, oh, this is just multiply by radical 3, okay, that is awesome. You can do the same thing. That's what this is equal to as well. All right, so once I find x is 31.2, that means this is 31.2 and this is 31.2. So overall, I get a 62.4 for my entire side length. This is our organization box that helps us stay on top of what we're looking for, because we're doing quite a bit here to make sure that we're finding overall the area. Once I have side length and apothem, that's my base of 62.4 and my height, 18, divided by 2 for this whole triangle. And I want 3 of those to make the entire figure. When I multiply that out, I get an area of 1,684.8, and this is measured in millimeters squared. And our last one for this section, all right, so we have a 1, 2, 3, 4, 5-sided object, so there'll be 5 triangles in here. Take 360 divided by 5 to find that central angle. That'll measure vertex to center, center to vertex. So this entire measurement is 72 degrees. Side length. Okay, so notice that all three of the examples here, we have an unknown side length, but we have a known apothem. So they gave us the apothem. That's to the center perpendicular. So again, we're going to focus in on our smaller triangle here. That's apothem radius and half the side. And so when I look at this, drawing it down here, I know that we have a side length here of 10. And if all the way across is 72, divide that in half to make this 36. Now I'm ready to find this missing piece here because it'll match there to get my entire side length. So 36 here, x is opposite and adjacent. And even though we've changed numbers and changed angles, we're still using the same tangent. So there's definitely a pattern here. And that'll be x over 10. Multiply, we get x equals 10 times tangent of 36, which gives us an x value of 7.3. A really common mistake is somebody taking this and thinking it's a side length. That's not true. This is only half of our side length. So a common mistake is hurrying and not writing it down properly and finding the double of that to make the entire piece here. The 14.6 is our entire side length. Once I have these two pieces, I can find the area. I have a base, that's the 14.6. We have a known apothem height of 10, and I want 5 of this triangle inside of the figure, where there's 5 of them here. 1, 2, 3, 4, and the 5 that we're focusing on. So when I plug this in, I get 365 with a units of inches squared. Number 4 on the next page. So we have a 1, 2, all right, I have to count. 1, 2, 3, 4, 5, 6, 7, 8 sided object. So there'll be 8 identical triangles inside of this octagon. Central angle we can find 360 divided by 8, which is 45 degrees. Side length, is given, so that's different. So we have a side length of 5 and an apothem that's given, that's 6. So we're not missing anything on this one. They've given us all the information that we need here. We can go ahead and go straight to our area formula because we have a base for our triangle, an apothem height, and we know how many triangles we need inside that figure. So I didn't need to do trig or special right triangles here. I could go straight to our formula. 5 times 6, 30, divided by 2, 15 times 8. Grab your calculator, we get 120 kilometers squared. And on 5, this last one here, okay, how many triangles? I have 1, 2, 3, 4, 5, 6, 7, 8 again. So another octagon. So the central angle, just from carrying it down from number 4, will still be 45. Side length of 14 and ruts. We don't have the apothem. So here I'm going to draw in my 2 radiuses. We know every side length is 14. But now what I don't know is this value. So one of the things that we do know is that across, all the way across here is 45. So this one's different. Now instead of missing the side length, we're missing the apothem, but it still comes down to that same triangle. So I'm going to take this triangle out and label what I know about it. I know that this angle is 22.5 because I have to divide this in half when I drop in the apothem. This is the apothem that I'm looking for, and then this length, well, it's not 14, but it's half of it to make it 7 here and 7 here. So now I can do circle and label opposite and adjacent, and it's still trig, so we still have our tangent now of 22.5 will equal opposite over adjacent. So we're still using the same tangent, but now we have a different unknown because our first cross doesn't get x by itself. We're going to divide by tangent on both sides to find what x is. And when I find this on my calculator to the nearest tenth, I get 16.9. And now I don't have to do any doubling like I did for the sides. That is my apothem. So now I can find the total area. I have a base, the whole side length is 14. The height of my triangle is 16.9. Divide by 2 because it's a triangle. And I want 8 of these identical triangles. So in my calculator, I get an area of 946.4, and our units are meters squared. So let me know if you have any questions as you're going through these, as we did practice, several different things that we could be given. And on our next section, we'll do these again just to get some more practice in as well. Hope you have a good day.